We can refer from the title, our paper aims to obtain precise pseudo-semantic segmentation ground truth using weak labels only and train semantic segmentation model with it. Here is the motivation and realization of our method. If we can measure the preciseness of the CAM or semantic segmentation, we can obtain better pseudo-ground truth. From this need, we try to measure the preciseness through inferability between segments. Ideally, if the object segments are well decomposed, we can infer the color or texture of one segment from the other. However, bring this inferability characteristic to weakly supervised semantic segmentation is not easy. The only possible label is classification label and image itself. We approximate the inferability as reconstruction capability. Likewise, the inferability, if one segment is precise, Reconstructor fails to correctly reconstruct the other segment. Using this, we build a framework that trains the classifier and Reconstructor adversarially. The classifier learns to generate precise CAM that can fool the Reconstructor while competing with each other. So weakly supervised semantic segmentation use CAM of the classifier to obtain pseudo ground truth from image level class tables. However, a classifier tends to focus on shared visual pattern, so the resulting CAMs highlight the discriminative regions of the corresponding class. Although CAM is a reasonable localizer extracting spatial information from semantic supervision, but in the perspective of semantic segmentation, CAMs still have several issues. The one is incomplete activation, and the second one is imprecise boundary. Here's the method. If we can measure the preciseness of the semantic segmentation, we can use this property to improve CAM. Then how can we measure the preciseness of the semantic segmentation without using ground truth map? Let's take a look at these three samples. The left one is when segmentation for the cat is precise, the middle one is under activation, and the right one is over activation. In the blue cases, we can infer the color or texture of the other segment since there is no proper information left. However, for the red case, we can infer the outside region somewhat correctly using the given information. So the inferability between segments can be a measure of the preciseness of the semantic segmentation. For the precise segmentation, inferability between the segmentation is low and vice versa. Then, how can we bring this property into weakly supervised semantic segmentation? Here is the second key idea. If one can infer color or texture of a segment from the other segment, the segment could be reconstructed from the other segment. Image reconstructor relies on neighboring pixels to reconstruct the masked pixels. Reconstructor can use remnant as reconstruction cues. In the blue case, we assume Reconstructor is well trained. We fail to correctly reconstruct since the given image is precise segmentation. In the two right cases, we can somewhat reconstruct the region with the given region since there is some remnant information. So we can regard the reconstruction capability as error between the input image and the reconstruct image, and we can quantize or using as a measure for the inferability. Train CAM to segment the image into segments that make reconstruction fail to impede each other. But how can we obtain such reconstructor? Similar to GAN, a classifier and a reconstructor are jointly trained in an alternative manner. The target CAM of the classifier decomposes a feature into two segments, target and non-target. The goal of the reconstructor is reconstructing the input image from the segment by fully exploiting the remnants. The goal of the classifier is making the reconstructor fail by providing good CAMs that achieve precise segmentation. Here, we devise a concept named stochastic remnant feeding, since the purpose of adversarial learning has a risk of falling into an undesirable local optimum. As the classifier trained, the classifier succeeds to provide precise cam. Then the segmentation becomes perfectly done. Then the reconstructor tends to generate the original image rather than the learning how to exploit the remnant. So we devise a stochastic remnant feeding technique to assure the existence of remnant by feeding synthetic remnant. Here's the example of how we generate stochastic remnant feeding technique and synthetic remnants. So the rightmost figure is the segment after SRF. So for the experiment we conduct on Pascal VOC and MS Coco, which is most widely used dataset in weakly supervised semantic segmentation, and mean intersection over union, mean IOU, is used. And the backbone, for the backbone we use ResNet 38 dilation, and the protocol is like this. So here's the qualitative result. These results are from baseline, and this is the CAM result obtained from ours. So more precise and high quality CAMs can be obtained through our method. So these are another sample from Coco. For the dog class, more precise can be obtained. To show the effectiveness of the proposed method, we conduct a relation study regarding adversarial learning and SRF. Without adversarial learning, by bringing the pre-trained reconstructor and incorporate with classifier, we can achieve some performance gain. When we train the classifier and reconstructor adversely, we can get meaningful gain. However, as we mentioned earlier, as training proceeds can become precise, then reconstructor try to memorize the dataset. So we divide SRF, and as shown in the table, much more improvements are made. With the proposed method, we not only achieve state-of-the-art in pseudo-GT level, but also achieve state-of-the-art in semantic segmentation level. By incorporating our framework with vision transformer, we also achieve state-of-the-art.